Thank you. Give me just a second to get my presentation going. Start myself a timer. All right, so I will go ahead and introduce myself first. I'm Riley Hales. I'm a researcher at Brigham Young University. I have been working on the GEOGloWS program for about 5 years here. Let's see. I recently finished a PhD. Just actually formally graduated just 2 months ago, so fresh out of that. I've been working on this sort of large-scale hydrology modeling for flood early warnings and flood mapping and such for the whole 5 years that I've been part of GEOGloWS and during my PhD. I'm going to be presenting on what we started to refer to as GEOGloWS 2.0. It's our next generation hydrologic model. If you looked at the emails earlier announcing this presentation, I mentioned talking about bias correction activities and some of the modeling improvements and lessons we've learned in doing large scale modeling. And so I'll be talking about all those sorts of things in the context of how we've improved our model and to do flood warnings and that sort of information more sustainably and more accurately. Hold on, there we go, now my slides are moving. GEO and GEOGloWS is a very large organization. So I'll start by recognizing there's lots of people that go into this. This is much more than just me, just Brigham Young University and all the people that I work with here. And though I can't recognize them all, I want to recognize the great network of people that comes together to make this possible. For those that don't know about GEO, GEO is a partnership of governments and all kinds of organizations that are looking for that elusive future where we make the best decisions possible using all the best data, particularly Earth observation data. And specifically for GEOGloWS, that's the Global Water Sustainability Program. We're looking for both direct Earth observation data from satellites and all the modeling and things that can be derived from those sorts of products. This hydrologic model that I've been mentioning gives forecast and hindcast river discharge at about 1 million places around the world. And for those that are probably more familiar with a product like GLOWFAST, we use a lot of similar data sets to GLOWFAST. So I'll informally say our model is a cousin to GLOWFAST. Our results are quite similar. So we'd be in that same family of models using a lot of the same data sets. So specifically what I'll cover is the GEOGloWS capacity building approach. We're not the only ones that work on global modeling. We're not the only ones that work on capacity building, but we try to have a unique approach that leads to some longer lasting and hopefully more meaningful, far-reaching impacts. Some of the successes that we've had with our approach, but where I'll spend hopefully most of the time, if I don't get carried away talking, is on the lessons that we learned throughout these exercises that led to improvements in our model and what we hope to get to in the future. So I've got this 5-step easy process for anyone to use science to solve their problems. Of course, it's never quite that easy, and I've changed some of the wording in these steps to match more of the kind of scientific problems I work on that involves collect data, build some sort of model, and do analysis. And the kinds of countries we usually work with are in need of this sort of information, whether because they were just hit by a disaster, maybe a hurricane just came through, or they're not as developed as they'd like to be, and then so they don't have the capacity to do this 100% independently. So these are the kinds of steps they're going to need help getting through. That'll start with find all your input data. And that's not necessarily a trivial step anymore, but it's pretty well doable for anyone to get access to free data sets that you'd need to answer these sorts of questions and on flood related matters to give flood early warnings. So I'm going to say that help usually starts just after that. And if you apply for help from the World Bank or from any number of capacity building or organizations, the bulk of the help they offer you is going to end up being centered on these next two steps, helping you get your personnel trained, buy the equipment that you need, build your numerical model. And I want to emphasize from the beginning that this is like the gold standard. In a perfect world, GeoGloWS maybe doesn't need to exist because all of these programs are infinitely successful, and the people that receive this aid can institutionalize the capacity. But that just doesn't always seem to be the case. There's a lot of really difficult challenges along the way. So where GeoGloWS hopes to be a little different is, rather than focus on that semi-permanent problem of training and buying equipment and building the numerical model, we're going to handle those ourselves. So that's a challenge that GeoGloWS can institutionalize and take on, and instead try to focus just on giving access to the data, making it usable and understandable, so that step all the way on the right, making the better informed decision, is possible to those people that need that have that burden placed upon them. Another way that I might describe this, if you take that concept and go up to the global scale, is instead of trying to get everyone to build their own local model, which again would be the gold standard, it would be great if everyone was capable of that. But since it's not, we're going to try and do move the modeling components onto the left, which is what we can handle as diagrammed on the bottom, and hopefully figure out a way to make these three pretty blue arrows that make all the model data sets easily accessible, so you can make better decisions using the data that we produce. And there's really two challenges to that. You got to make a model that's good enough, and figuring out what constitutes a good enough model is a tricky to define concept all on its own. And what kinds of services do you need to make to in order for your model to be accessible is another challenge all into its own. And so I'll just briefly cover those and move on to some of the lessons that we've learned with this approach and the success stories. Specifically, some details on what we provide with our hydrologic model is hindcast and forecast data sets. The hindcast is daily average flows beginning in about 1980, and the forecasts cover 15 days and generated every day. The hindcast is deterministic and the forecast is an ensemble forecast. Again, these are because we use a lot of the same forcing data sets as produced by ECMWF, our European partner. These sorts of graphs will look pretty similar to products that you would see from GLOWFAST or EFAS. Sorry, I got ahead of myself. We have a bunch of data services that makes this accessible through code, through web interfaces, web apps. And in addition, there's a mapping service. And this is an animated service. You can see on the bottom, there's a time slider. So the styling of the rivers changes throughout the course of the 15 days. The coloring indicates whether or not you're exceeding a return period, or you're expected to exceed a return period more precisely. And this is available, again, for free on the Esri Living Atlas service. So any GIS software or anything that will ingest web maps can use this layer for free. So I'll move on now to what's the success we've had with this approach. Now that the map we're looking at on the left has some really funny shapes in it, and we've been collecting analytics on who uses our data, and due to some challenges in getting all the data out, what we're looking at is a semi-random sampling of all of the data sets. It's not perfect, so you see those fun banding artifacts because we didn't get the whole data sets of analytics sent to us. This is a sample of it. But over the period of June of last year, 2022, to January of this year, so 8 months, we had right about 4 million requests for data, which if you scale that up is about 6 million a year, or something in the neighborhood of 16 to 17,000 requests per day. And so that's a huge number. We are always kind of blown away to look at these maps and see the numbers. The the dots that we're looking at on the map are the locations of the river where data was requested for, not the location of the person asking for the data set. So there's been interest in data pretty much all over the world. And we're happy to know also that we've worked with people in a lot of these countries, and so it makes sense to us where some of those users come from. But there's also lots of places where we have not worked with people, but we see there's lots of requests for data to see that this has reached people beyond just who we talk to. One particularly relevant success story for the GFP is a use case in Malawi. They had a community-based flood early warning system, that CBFuse up at the top. And there's a graphic of their web app in the center of the slide. So they have measuring stations along the river. And if you're upstream of someone and see that the water's starting to rise, or you just got flooded, you can alert all the people downstream, there's a flood coming, brace yourself. And so you've got something on the order of hours, not days, definitely, to prepare yourself, evacuate if that's necessary, based on this sort of community system. And on the left, you can see that this has been getting ahead of myself. So with GEOGloWS, we offer 15-day forecasts. So we've been able to work with them a little bit to help them use this information to extend their warning times, as is quoted on the bottom, from hours to days. That's a quote from Samuel, who's pictured on the right, presenting about this at COP26, I believe was the meeting. And this has been very successful. Obviously getting something like 30 times as long lead times is a huge increase in forecast warning times for floods. That gives you a huge amount more time to position resources, decide if you need to evacuate, alert emergency responders, that sort of thing. Another use case of this comes from Honduras. This is in November, I'm pretty sure, might be October of 2020. There was Hurricanes Eta and Iota. And Honduras did not have particularly well-developed river monitoring capabilities upstream of this dam. And so when the first hurricane came through, it disabled those gauges. So Hurricane Iota that came, I want to say, about 2 weeks later. So it was really about as close as you can get back-to-back hurricanes. They were flying blinds and needed information on what should we do with this reservoir? Do we need to start releasing so that we don't overtop? All those sorts of questions that a reservoir manager would be familiar with were really important to them, because they just had a big hurricane come through, so the reservoir filled a lot and were uncertain how much to expect. Excuse me, when the next hurricane came through. And so using GEOGloWS, we were able to help them get some forecast information. And to grossly oversimplify a lot of validation work that was done after the fact, our forecasts were pretty good. We're looking at hydrographs on the right from a few of the places upstream and downstream of the reservoir where we still were able to get observed values and compare it to what we forecasted. And we did pretty well. And it's always, I'm grateful to say that we didn't have to find out if we were right or wrong, and the dam did not overtop, and we averted loss of life and everything. So hopefully with these two examples, just want to quickly illustrate that there's been really wide-reaching applications of GEOGloWS throughout the world. And with some friends at the World Bank, we've been able to have similar kinds of stories throughout South America and Africa, and really many places throughout the world. So I don't have time to share all of them, but in these use cases, we've learned an awful lot of information. And so I'll move now to trying to talk about some of the lessons that we've learned from these, because as modelers and as in the scientific world, we know what we think is important about building the models, and we want to make our error metrics look as tiny as possible. And I can conceive what I believe is the most important way to convey information, but I am not the city council member or as some local government official on all these places. And so that it's the information that we've gained from these collaborations has been really valuable. And so I'll sample just a handful of them and how we took this information and used it to improve the model such that all the local stakeholders and decision makers hopefully have an easier time using this information to and can use it more as a permanent fixture of the capacity that their institution has. So first I'd say that imperfect models can still be useful if we can understand their inaccuracies and understand therefore what the model would be good for. That this is again something that's different from the scientific crowds that's I'm part of that we're so focused on to make sure my error metrics are down to zero, zero error. I want to have perfect predictive ability, even though that's a elusive and perhaps sometimes unattainable goal at the moment. We got to work with what we're able to provide, and an imperfect model can still be useful. Second was that there's this concept that the local agencies need to have some sort of ownership or branding ability over global data sources, which I'll elaborate on. We need a better stream network for a wide number of reasons. What we currently have is something in the neighborhood of hydrosheds. It's not exactly any of the resolutions of hydrosheds, but they're delineated from the same source data, so that our resolution and the positioning of the different subbasins is slightly different, but very similar. So that for a good number of reasons, we wanted to improve the accuracy and density of those stream points. And fourth is one that resonates more with me, of course, that you want better flow magnitude predictions so that our imperfect model has fewer of those imperfections and the number of applications potential increases. And then last is we want to have status and outlook products. The WMO made a challenge, I believe it was earlier this year or late last year, saying that we want everyone in the world to have access to early warnings. This is the early warnings for all challenge, saying that everyone should be able to have some notice on when a flood is coming. Everyone should have the ability to do something to prepare. So that's a relatively new addition to a new lesson that we've learned, is how do we condense our information into a way that's digestible in that context. So I'll go one by one and elaborate on these just a little bit more. First, the imperfect model can still be useful. If we can find ways to validate our results before and after bias corrections, which I'll talk about in number 4. And if we can group our performance based on stream order or by predominant lands cover type, if we can learn some of the errors or places where we usually have error, or if we can learn some of the places that we usually do really well and you can trust the results as is, no further modifications needed, that better increases confidence on whether or not you can trust the specific volumes of water that we're forecasting. I've also got a zoom in figure of that same map in South America. These dots we're looking at are places where we are able to get some amounts of gauge data, and before and after bias correction, which again, I'll talk about more afterwards, we're able to increase the performance of the model, which obviously increases confidence because we can validate and do some local calibration of the data sets. Another way that the imperfect model can still be useful is we found that we have pretty good skill in predicting whether or not the event will occur. Not so often are there false positives or false negatives, even if the magnitudes are incorrect. Turns out that if we tell you the flood's going to be 11,000 cubic feet per second and it's actually 10,000 cubic feet per second, you can still make the same decision if you are an emergency manager or a government official or something like that. Particularly as scientists, we latch onto the numbers, but you can still learn to interpret forecasts and deal with uncertainty, even if the precise value is not 100% correct. So we've developed this serious game, is what we call it, to walk through a artificial scenario where we have these graphs and we tell you this is the day that the our meteorology tells us the storm is going to hit on this day, so we're going to watch our flow forecasts over 10 days or 15 days, the whole period of the forecast, and watch how the uncertainty varies and how different parts of the forecast become more meaningful to you at different parts of the 10-day lead time. So this has been a great way to train people to use this sort of information. Second is that the local groups really need a way to own their information. These groups often have a legal mandate to provide the kind of information that we're trying to assist them in providing, but they can't just pass the buck off, so to speak. They can't just say, all right, we're going to fulfill our job by telling you to use someone else's hard work. So they need a way to collaborate with us, to get their own copies of the data set, to really internalize why this is working the way it is, why do the results say what they do, perhaps redistribute the data through a web domain that they own or a customized interface. So we do a good amount with that in that area. And with a collaboration with Amazon Web Services between Geo and AWS, we're able to give the countries that we work with 2 years of credits, and I'm spacing on the exact dollar amount, but it's enough credits such that they can run their own copies of these tools if they would like to do any other related processing to these data sets. And it also gives them some access to IT support so that they can figure out, if I optimize this the best possible, what would be the cost for me to do this? If once the 2-year credit is up, and if we really want to carry on with this approach. And this is a relatively new addition to the things that we work on, but it's been very important and impactful. So we're excited to see where this goes in the future. Third, you need a better stream network, and I think it's speaking largely to the scientific crowds, particularly in the Global Flood Partnership crowd. We'll all appreciate that more accurate stream networks has a lot of implications for how well you can predict floods. If you got to get the location of the river right so that it aligns with the DEMs and such. I talked about how we're currently pretty similar to hydrosheds. We're going to start using the TDX Hydro data set. That was a recently released product from a US science agency, the National Geospatial Intelligence Agency, NGA. That has 16 million points, subbasins, subriver units. We're doing some post-processing on that, so it's not exactly the original TDX Hydro data set. We're cutting down some streams and doing some dissolving, such as at the headwaters. Turns out there's a huge number of stream order ones. So on the left, each of the segments that show up separately in the original data set is colored uniquely. And on the right, so we're doing some dissolving to end up with a few less stream segments at the headwaters. Lots of processing has gone into this, particularly in the last like two and a half months for me. But we're very excited to pick up this new data set. This has lots of obvious benefits for flood mapping. These are some flood maps generated from different methods that we've worked on. On the left is in the Dominican Republic, and on the right is in Brazil, I'm pretty sure, if I'm remembering my source material well. I'm pretty sure that's from a river in Brazil. And we're really just starting to scratch the surface since we're barely implementing the TDX Hydro data set, but obviously lots of exciting things for switching the stream network. Looking down at my time, I've droned on just a little too much, so I'll speed up through the last bit here. We want to do, of course, better flow magnitudes, because that opens the door for better accuracy overall, but also it allows for other sorts of applications where that are really sensitive to the exact flow magnitude, such as water quality or operating reservoirs on a longer scale than just in emergency situations like in Honduras that I talked about. So we're using a bias correction method that relies on flow duration curves. On the left, we've got pictured a modeled and a observed flow duration curve. So the blue one being the modeled and green is observed. We've done a frequency matching technique so that you can substitute flows based on matching exceedance probabilities. Something that's pretty new that's going to get a GEOGloWS wide release in the coming months is a way to expand that to all engaged basins in the model. We create the ratio of the modeled and observed flow duration curve, and that's what's pictured on the right. Just divide the two. Now moving on, that's on the left, I've added some labels. This ratio of the curves, as you repeat that over a large series of months, and for all of the gauges that are available at different seasons throughout the year, together these curves characterize throughout time and space how biased your model is. And the question then becomes, how do I know which of the ungauged basins shares that same bias profile as described by these curves? So we use a combination of machine learning, lots of remote sensing data sets to classify watersheds. That's a very typical problem in hydrology. Can you figure out which basins behave similarly? And then we can use this series of curves to correct by that ratio of the curves, all of our flow magnitudes. And last, we are starting to work on creating status and outlook products, and EW for All is the WMO's Early Warning for All challenge. Again, this is pretty new, but what we're looking at is a map of in each subbasin of our model, is the flow in that basin currently for the month, is that above, below average, is it normal, by comparing that current month's flow to its entire 1980 to 2022 period of record on our simulation. And we're starting to make some fun animations showing how this changes over time. This is a very new area we're excited to keep diving into. This is particularly important to the WMO and the international crowd. So to summarize, we're very excited to see that GEOGloWS has had such a wide-reaching impact, despite the many challenges in global modeling that I work on particularly a lot. We found that there's lots of lessons to be learned when you bridge the gap between the modeling crowd and the local users of your model. And if you're looking for lasting impact and sustainability, you got to have that line of communication open, got to work together to figure out what the local implementers of your data really need. So we've tried to take as much of that feedback as possible to create our next generation Streamflow products to make it more accurate, better fitting the needs of the local users. And the last thing I'd chip in there is document your attempts to do so, no matter what your specific research area is. Document these because they tell good stories about what is the best way to go about bridging this modeler to decision maker gap, which is a pretty wide-reaching problem all throughout the world and through all groups. This table just summarizes the changes that we made, but thank you very much.